的各位老师、各位同学，大家上午好，欢迎参加第12期 Undervisions 青年学术论坛。我是本次论坛的主持人，来自天津大学的李鹏，同时也是 Advances in Applied Energy 的主题编辑。今天我们非常荣幸的请到了 Cornell 大学的尤冯奇教授、博士生赵宁同学来介绍他们课题组的工作。赵宁同学主要从事基于优化和机器学习的能源系统低碳规划方面的工作。他之前的研究项目包括能源激励政策设计、不确定条件下的低碳规划、多尺度可再生能源转型优化。本次报告的题目是 New York State's 100% renewable electricity transition planning under uncertainty using a data-driven, multi-stage, adaptive, robust optimization approach with machine learning。这个工作呢，也是去年发表在 ADAPN 上，欢迎大家下载阅读。ADAPN 呢是 Applied Energy 的姊妹刊，致力于发表能源领域跨学科高质量的研究工作。它于2021年创刊，创刊主编是严进月教授。在1年多的时间里 ，ADAPN 共发表了90篇文章。目前根据 Google Scholar 的统计，我们已经获得了1000多次的引用。借此机会，我也诚挚希望大家能把好的、有意思的工作投到我们的期刊。当前在能源领域研究的问题中，100%可再生能源电力系统一直是学术界和工业界为之努力的和奋斗的一个重要方向。我们国家也提出了3060碳达峰和碳中和的目标，而基于数据驱动的人工智能方法也是当前备受广泛关注的热点工作。当机器学习方法遇到100%的可再生能源系统，会发生何种奇妙的化学变化？让我们期待赵宁同学的报告。下面欢迎。
谢谢刘老师。这个报告的部分我就先用英文做这个报告，然后大家如果都是中国人的话，之后可以用这个中文进行一个交流。Hello everyone, this is Ning. I'm a Ph.D. student in Professor Fengqi You's group at Cornell. The topic of my talk today is New York State's 100% renewable electricity transition planning under uncertainty using a data-driven, multi-stage, adaptive, robust optimization approach with machine learning. Climate change has become a critical issue that attracted global attention for years. In fact, the past decade was the hottest on record, and this is the latest sign of global warming on the planet. Globally, 2021 ranks the 5th on the list of hottest years on record, warming than 2015 and 2018. And the annual average temperature rise of 2021 set at 1.1 to 1.2 degrees C above the pre-industrial levels of the 20th century. And this is caused in large part by emissions of carbon dioxide and other heat-trapping gases from the burning of fossil fuel. And the CO2 concentration in the atmosphere is currently at the highest levels for over 800,000 years. So the global energy-related carbon dioxide emission increased from 2 gigaton per year in 1900 to 36.3 gigaton per year in 2021, which is the highest level for annual greenhouse gas emissions. Compared to 2020, the number rose by 6% because the world economy rebounded strongly from the COVID-19 crisis and relied heavily on the coal and other fossil fuels in order to power that economic growth. Unfortunately, from the numbers in this figure, we can find that this increasing trend of such greenhouse gas emission is not so optimistic. To enforce the global response to the threat of climate change, the United Nations has reached the Paris Agreement. It aims to keep a temperature rise in this century below 2 degrees C above pre-industrial levels, and to pursue efforts to limit the temperature increase even further to 1.5 degrees C. However, given that temperature in 2020 was already 1.2 degrees C higher than pre-industrial levels, one can say that this world is far from meeting these targets. In this figure, we can further look at the challenges in front of us from a prediction perspective. The potential greenhouse gas emissions and the predicted temperature rise under uncertainty are presented for this century. A key feature in this figure is that the uncertainty can considerably influence both the greenhouse gas emissions and the temperature rises. So it is important to consider the uncertainties while planning for the future. In terms of the different cases, we can find that with no climate policies, the emissions are likely to skyrocket to over 100 gigatons by the end of this century, and the temperature could rise by 4 to 5 degrees C. On the other hand, involving some climate policy could lead to a temperature rise of 2 to 3 degrees C, and the lower levels of emission compared to current status. If the world aims at achieving the 2 degree C long-term temperature target within the 21st century, zero emissions or complete decarbonization seems to be a promising and inevitable approach. Therefore, effective and bold action is needed if the world intends to achieve these targets proposed by the Paris Agreement. The decarbonization policies from administrations are especially needed. To this end, New York State has the ambition to combat climate change. It has passed a sweeping climate plan in July 2019. It's called the Climate Leadership and Community Protection Act. So several ambitious and major targets of the CLCPA include producing 70% of electricity from renewable sources by 2030, reducing 100% of electricity sector's greenhouse gas emission by 2040, and eventually achieving net zero emissions in all sectors of the economy by 2050, which is 30 years from now. President Biden also announced ambitious climate targets for the power sector, such as achieving an emission-free power sector by 2035, installing millions of new solar panels and tens of thousands of wind turbines, etc. And from the previous prediction figure, we know that the uncertainty could have great impacts on power systems transition. And a knowledge gap exists in addressing the renewable electricity transition optimization under this uncertainty, while considering the sequential decision-making process under multiple time periods. In other words, the uncertainties of all time periods are not realized at once. It's a more realistic assumption is that the uncertainties are realized in each time period. Here shows the sequential decision-making process for multistage adaptive robust optimization, MARO. And XT here represents the decision variables in each time period, and UT represents the system's uncertainties. The uncertainties are realized in each time periods, and the values of decision variables are then determined subsequently. The sequential approach could effectively and efficiently utilize the uncertainty information and tends to generate less conservative solutions compared to conventional static robust optimization. The decision variables before uncertainty realization are here and now decisions, while these decision variables after uncertainty realization represent the wait and see decisions. There are two main goals of this study. The first is to develop a bottom-up modeling framework for 100% renewable electricity transition that accommodate climate targets, scheduled system changes, as well as sequential decision-making process. The framework should be capable to integrate machine learning-based data-driven approaches to handle the system's uncertainties. And the framework should also be general enough so it can be applied to any other regions in the world. The second goal is to propose the potential power systems renewable transition pathways under multiple electricity systems uncertainties. And the network framework figure here represent the power systems for this study. It shows electricity flows and emissions of the power sector. The system is supposed to meet the electricity generation demands on an annual basis. In terms of power generation, electricity can be generated from both renewable and non-renewable technologies. Renewable sources include hydro, solar, and wind, and solar power includes the utility and distributed solar PVs. Wind power can be categorized into on-land and offshore wind. Non-renewable energy sources include fossil and nuclear. So the power systems model is formulated in a bottom-up manner that characterizes each power generation facility by its generation technology and its age. And this can be more appropriate for integrating the energy transition process, which is directly related to the active technologies and facilities. The electricity are produced and transmitted to be used for multiple end uses, including residential, commercial, industrial, and other power end uses. A proportion of electricity may be stored before its usage. This is necessary for the stability of the grid, since a lot of electricity would be generated from intermittent sources such as wind and solar. The system's uncertainties and decision variables are realized and determined on an annual basis, which reflect the sequential decision-making process. The figure on the bottom left shows the uncertainty data samples in one time period, considering that we have we have 15 time periods across the planning horizon. The power systems uncertainty in this study include the electricity generation demand, the market availability of wind turbines, and the market availability of solar PVs. Based on the uncertainty data, machine learning techniques are used to construct the data-driven uncertainty sets, which facilitates the subsequent optimization step. The machine learning techniques applied in this study include a variational inference algorithm for Dirichlet process mixture model, DPMM, principal component analysis, and kernel density estimation. Given the power systems formulation and the uncertainty set structure, the renewable power systems transition under uncertainty can be formulated into a multi-stage adaptive robust optimization framework, MARO. Note that the MARO problems are computationally intractable because of its multi-scale structure and the semi-infinite constraints. Therefore, affine decision rules are applied to reformulate the MARO problems into its more tractable robust counterparts. After computational optimization, we could have the potential renewable electricity transition pathways under uncertainty, such as annual electricity generation from different energy sources and technologies. This is the structure of the MARO power systems renewable transition framework proposed in this study. The objective function is to minimize the total electricity transition cost under uncertainty. The total electricity transition cost consists of capital cost, O&M cost, decommissioning cost, importation cost, and also carbon tax. The uncertainty, as mentioned previously, include the electricity generation demand, the market availability of wind turbines, and market availability of solar PVs. The min-max here in the objective function is a simplification of the original multi-level optimization structure. And here we can find X and U represent the decision variables and the uncertainties in each time periods respectively. Sorry. The objective function is subject to multiple types of constraints. For instance, the renewable electricity generation and emission targets constraints represent the technological and climate targets, including net zero emission targets, renewable electricity percentage target, carbon-free electricity targets, emissions target, and also renewable generation technology deployment targets for intermittent renewable sources and also energy storage. The scheduled systems changes constraint include the scheduled additions of generators, scheduled decommissioning of generators, and scheduled additions of storage facilities. And here we show a general form of the uncertainty set formulation. Here we can find U denotes the uncertainties and V represent the auxiliary variables if needed. The proposed renewable electricity transition MARO is computationally intractable owing to its multi-level optimization structure and semi-infinite constraints. And semi-infinite here means that we have a finite number of variables and an infinite number of constraints because of the constraints defined by defining the uncertainty sets. Therefore, the affine decision rules are adopted to reformulate the MARO into its tractable, robust counterpart based on duality theory. Specifically, the affine decision rule replaces the wait-and-see decision variables by the affine functions of these uncertainty realizations. And the coefficients of these affine functions are introduced as new variables, as shown here. To illustrate the applicability of the proposed electricity transition framework, a case study on the 100% renewable power systems transition of New York State under uncertainty is investigated. The main climate targets include the 70% renewable electricity generation by 2030 proposed by the New York State CLCPA, and achieving an emission-free power sector by 2035, according to the National Climate Plan of President Biden. And the technology deployment targets for renewable generation and electricity storage are also included. 5 cases are investigated based on the formulation of the uncertainty set, including deterministic planning, box uncertainty set, budget uncertainty set, data-driven uncertainty sets using variational inference algorithm for DPMM, and data-driven uncertainty sets formulated using PCA coupled with KDE. Specifically, the deterministic planning case includes no uncertainties, so its optimization results are not robust and cannot fully hedge against the worst cases during the power system's renewable transition. And the table here shows the features of different cases in this study. The deterministic planning considers no uncertainties, and only the DPMM and PCA coupled with KDE uncertainty sets are data-driven uncertainty sets that are constructed using these machine learning techniques. 4 types of uncertainty sets for the year of 2030 are visualized here. In this figure, the x-axis, y-axis, and z-axis represent the uncertainties of annual electricity demand, market availability of wind turbines, and market availability of solar PVs, respectively. The box uncertainty set and budget uncertainty set for 2030 are showing in the top 2 figures. Both types of uncertainty sets are not data-driven uncertainty sets, and all data samples are included in the box or budget uncertainty sets. On the other hand, the bottom 2 figures visualizes the DPMM uncertainty set and the uncertainty set using PCA coupled with KDE for 2030. These data-driven uncertainty sets are tuned to have the same coverage level of data samples, which is 90% in this study. In this figure, the data samples included in these data-driven uncertainty sets are plotted using red dots, while the samples that are not included are represented by the red crosses. In terms of computational optimization, both the deterministic planning and robust optimization of the transition problem in New York State are coded in GAMS. The deterministic planning and reformulated MARO problems are solved using CPLEX 12 with an optimality tolerance of 0%. The optimal objective value and the solution time are 2 main metrics for evaluating an uncertainty set. The optimal objective value is represented by the minimum power systems transition cost, so smaller objective values are preferred, while the solution time stands for the execution time of the optimization program, so shorter solution time is preferred. The solution time of the optimization programs for different planning horizons are presented in this figure. Note that several factors can affect the solution time of MARO problems, including the sparseness, formulation, the size of the feasible region, and also the number of auxiliary variables. The deterministic case has the shortest solution time of less than 1 CPU second for all planning horizons, while the robust optimization cases tend to have much longer solution time. This is because the optimization problem for deterministic planning have significantly smaller problem sizes than the robust optimization cases, considering that a number of dual variables and dual problem constraints are introduced while we implement the affine decision rules for MARO. The budget uncertainty set for planning horizon 2020 to 2035 leads to the largest solution time. And this is likely to be resulted from its non-sparse uncertainty set formulation and its large feasible region for the uncertain parameters compared to the other types of uncertainty sets, as shown in the previous figure. And in comparison, the DPMM uncertainty set has a similar non-sparse formulation, but its feasible region for uncertain parameter is considerably smaller than that of the budget uncertainty sets, leading to a shorter solution time for longer planning horizon. Lastly, the uncertainty set constructed using PCA coupled with KDE has more auxiliary variables that may increase the solution time for even shorter planning horizons. But its sparse formulation and the relatively small uncertainty set feasible region combine to lead to less solution time under the planning horizon of 15 years compared to the budget uncertainty sets. The optimal objective values, namely the minimum renewable electricity transition cost under uncertainty for different uncertainty sets and different planning horizons, we show the results here. The deterministic planning solutions show lower electricity transition costs compared to the robust optimization results because the potential uncertainty realizations are not considered in these deterministic cases. The total systems cost for the electricity transition of robust optimization solutions are 21 to 42% higher than the deterministic planning. Considering the robust optimization cases, using data-driven uncertainty sets, including PCA and PCA coupled with KDE and DPMM, could achieve less conservative solutions compared to the conventional budget and box uncertainty sets, as shown by their relatively lower objective value. The total renewable transition cost under these data-driven uncertainty sets are 2 to 17% lower than the conventional uncertainty sets. In addition, the data-driven MARO solution could cover 90% of the potential uncertainty realization across the planning horizon, while the solution under the deterministic scenario could only cover around 24 to 57% of the potential uncertainty realization during the transition process. Therefore, we can address that using the robust optimization could effectively address energy transition uncertainties and benefit the reliability of power systems. The electricity generation from different sources during the transition under deterministic and robust optimization solutions are shown in this figure. We can find that the electricity generation for deterministic solution in the first figure is much lower compared to the robust optimization solutions shown in the other four figures. This is because the case under uncertainty could compensate for any potential realization of the uncertain electricity generation demands, which could be higher than the generation demands under the deterministic case for any time periods within the planning horizon. Notably, the annual electricity generation within the planning horizon may vary for different types of uncertainty sets. This is because the annual generation demand is an uncertain parameter, and the ranges of its potential realization are likely to be different for different types of uncertainty sets. The electricity generation under the budget uncertainty sets tend to be much higher compared to other types of uncertainty sets. And this can be illustrated by the previous figure on the uncertainty set visualization, which shows a higher range of potential realizations of the uncertain electricity generation of the budget uncertainty sets. In terms of renewable energy generation, Renewable sources provides around 80% of total electricity generation by the end of the planning horizon, that is 2035, for all deterministic and robust optimization cases. And wind may become the major source of electricity, mainly due to the relatively high capacity factor of over 20% compared to other renewable power sources. Notably, the major energy source for your power systems under deterministic and robust optimization cases are different. On-land wind may become a major source for electricity generation in the deterministic case in 2035, while offshore wind accounts for the largest proportion of electricity generation by the end of the planning horizon under the cases with uncertainty. The differences in the application of different types of wind energy for deterministic and robust optimization cases are resulted from both economic and market availability reasons. Economically, the capital investment of on-land wind turbines is less than offshore wind, but on-land wind turbines would need more investment on electricity storage units for unit amount of electricity generation. Therefore, considering that electricity generation demand for the robust optimization cases are much higher than the deterministic ones, the cost for electricity storage would significantly increase if on-land wind becomes the major renewable sources in these robust optimization cases. In terms of market availability, the offshore wind turbines have high capacity factors, so they would generate more electricity under unit amount of installed capacity compared to on-land wind. And this is particularly important considering that the market availability of wind turbine in these robust cases could be considerably less than the deterministic case, since it's an uncertain parameter. And due to these two reasons, on-land wind is selected as the main power source at the end of the planning horizon in the deterministic case, considering that this case has complete information about the annual generation demand and the much larger market availability for wind turbines. As for solar wind, distributed solar PVs account for a small percentage of electricity generation by 2035 for all deterministic and robust optimization solutions, while utility solar PV have a much smaller market share compared to distributed solar PV under all these cases. The relatively high penetration level of distributed solar PV is probably because of the deployment requirements from the government. This requirement mandates the capacity of distributed solar PV to be higher than 6 gigawatts by 2025, and no such requirements exist for the utility solar PV in New York State. On the other hand, the market availability of solar PV is much less than that of wind turbines, which suggests that it may benefit the application of solar power by increasing the market availability of solar PVs through increasing importation or domestic manufacturing. Hydro and nuclear power currently provides over half of the annual power generation in the state, and they would account for around 21 to 24% of electricity generation by 2035 for all cases. The generation from hydropower are relatively stable during the transition because of its long lifetime, and the major reduction from the nuclear power for all deterministic and robust optimization solutions are because of the scheduled decommissioning of large nuclear plants, and also its a relatively short lifetime. For example, 2 nuclear plants are scheduled to be deactivated in 2021, and the scheduled decommissioning can be observed in this figure for all solutions. In terms of fossil-based electricity, natural gas combined cycle would continue to be the dominant technology in the first decade of the electricity transition process for all of these cases. It is worth noting that the electricity generation from NGCC increased slightly during the first 4 years of the planning horizon for both cases with or without uncertainty involved. indicating that the natural gas plays an important role during the early stages of power systems decarbonization. The electricity generated from natural gas under the deterministic case would gradually decrease from the 5th year of the planning horizon and extinct exactly by 2035. On the other hand, the generation from natural gas would mainly be replaced by offshore wind 1 year before the end of the planning horizon for all solutions with uncertainty. In addition, although NGCC with carbon capture and storage is not selected for the deterministic solution, this technology may contribute to the electricity generation for robust optimization cases with all types of uncertainty sets. This suggests that the CCS may benefit natural gas-based generation technologies when developing more conservative power systems renewable transition plans. The accumulated total transition cost through the renewable electricity transition process for all scenarios are shown in this figure, and the accumulated total cost are normalized based on the optimal solution under the box uncertainty set. The cost for budget uncertainty sets are considerably higher than those of the deterministic solution, and the robust optimization cases with other types of uncertainty sets for all stages within the planning horizon. On the other hand, the deterministic case show much lower accumulated total cost in any time period within the planning horizon compared to the cost for all robust optimization cases. This is because deterministic solution would not accommodate the potential realization of these systems uncertainties. Moreover, the data-driven uncertainty sets, including the DPMM and PCA coupled with the KDE-based uncertainty sets, show consistently lower total accumulated transition cost during the planning horizon than those conventional uncertainty sets, such as box and budget uncertainty sets. This indicates that the data-driven uncertainty sets could lead to less conservative electricity transition pathways for any stage within the planning horizon, while it also effectively handles the power systems uncertainties. This figure presents the annual total greenhouse gas emissions in CO2 equivalent across the planning horizon. The emissions at the end of the planning horizon becomes 0 for all deterministic and robust optimization cases, indicating the achievement of carbon neutral electricity systems. The emissions in the deterministic case are over 10% lower than the cases under uncertainty. This is because the relatively low annual electricity demand for these deterministic cases, because deterministic planning does not need to address these potential uncertainty realizations of annual electricity demand. The case under the budget uncertainty sets has more greenhouse gas emissions at the early stage of the transition, and this is mainly due to its large feasible regions of the uncertain power load demand compared to other types of uncertainty sets. The potentially large generation demand requires more fossil-based electricity to compensate, considering that fossil-based power would be more economically favorable, especially during the early stages of the energy transition. Furthermore, the large reduction amounts of greenhouse gas emissions in the last 3 years are mainly attributed to the large market availability of variable renewable generation units, which is represented by their production amounts in the US. If smaller or more accurate market availability estimations are available, we can expect that this reduction of greenhouse gas emissions would be more steadier. The electricity storage capacities in each time period are shown in this figure. The case under the budget uncertainty sets again has the largest electricity stored capacity at the end of the planning horizon, because it has the largest generation capacity from variable renewable energy sources such as solar and wind. The deterministic solution has larger electricity storage capacity than most of the robust optimization cases, And this is because online wind is a major power source for deterministic case, while offshore wind contributes the most of the electricity under these cases with uncertainty involved. Specifically, online wind turbines tend to have relatively low capacity factors compared to offshore wind. So larger electricity storage capacities are needed for a unit amount of electricity generation from online wind turbines than those offshore wind turbines. Furthermore, the electricity storage capacities under the data-driven uncertainty sets are lower than the deterministic planning and the robust cases under conventional uncertainty sets. And this is mainly because the cases using data-driven approaches have relatively low generation capacity using variable renewable energy of solar and wind. And here we list the major conclusions of this work. And thank you for your attention. Your questions and comments are welcome.
非常感谢啊，非常感谢少宁同学的这个精彩的报告。有几个问题啊，有几个问题大家发上来的，想跟咱们一起讨论。就是第一个呢，就是有的内容可能是我们这个关于我们这篇文章的工作，有的可能也不局限于咱们这个文章的内容。首先呢，大家比较关注的一点就是说，对于纽约州的这个100%可再生能源电力系统这样的一个目标，是不是过于先进了？就是这个，因为现在在俄乌冲突的这样的一个背景下，我们也看到有报道说这个德国可能要放弃这样在2035年实现这个碳中和或者是100%可再生能源供电的这样的一个目标。那我们想问的是，就是说，那对于纽约州这个计划有没有什么变化，或者受没受这个能源的这样的一个市场的一个影响？
是，谢谢您的问题啊。首先，纽约州呢，怎么说？目前这个计划还没有变。然后，其次就是纽约州它有比较好的这个可再生能源的一个资源吧。然后，目前这个可再生能源还有核能就贡献了这个纽约州全州发电量大约50%到60%。那么是不好意思那么剩余40%的脱碳的这个部分呢，那纽约州也有这个怎么说呢？一个实施的一个计划。就比方说，太阳能发电是计划在2025年前达到6吉瓦，然后海上风力发电是在35年前达到我印象9吉瓦。然后此外还有对于 energy storage 在2025或者2030还有一个具体的一个规划，所以这个还是目前逐步在实施，起码。然后德国那面，反正我们知道就是天然气就跟国内不太一样，天然气在美国和欧洲电力系统的这个转型上起到一个比较重要的一个过渡作用。然后美国也是天然气的一个基本是最大的一个生产国吧。然后德国现在主要的一个问题也是从天然气进口方面有一些，因为俄乌冲突有一些阻碍嘛，所以就这个我们目前还不好说是不是一个短期的一个影响，所以就是只能说就希望他们的问题能尽快解决吧。然后纽约州还没有一个目标上还没有一个变化。
好，谢谢。
林老师，哎，我能问个问题？哎，林老师，我好，哎，那个，赵同学你好，哎，对，就是我有一个问题是有关你的模型的，那因为之前。因为这篇文章是我审的，所以那阵儿也有一个一直有一个自己的一个问题想问你，就是说你现在考虑这不确定啊，它其实你的这个不确定级，它是一个可以理解成它是一个 boundary， 但是就是说一般的数据它并不满足一个均匀分布，对吧？就是说越是复杂的东西，它是越应该是满足一个正态分布的。或者说在某些特殊的角度它是不同的这种分布形式，所以这样的话我觉得是不是在你们的这个考虑里，你们还是把它假设成一个在一定范围内的或者说确定范围内的一个均分布， 来去做这样的一些分析。那如果是基于这个角度来去做的话，那它的这个相当于，那首先有几个问题啊。第一个问题就是说，它的数据量的问题，因为你如果数据量不一样的话，它的 boundary 应该是完全不一样的。比如说你数据量很少的时候，它可能有一些边界的点它就探测不到。那这样的话，它的这个，我觉得你这个可能最后对你的形状的影响会非常大。然后你数据量比较多，或者说有一些误差数据的话，它可能对你这个你现在这个形状的影响也是非常大。所以就是说，第一个是对于这个数据质量，数据质量包括你的误差和这个数据的这个 size，对你这个方法的一个敏感性，一个是我感觉可能会有一些影响，或者说它这个敏感会比较大，这是第一点。第二点就是说，那在这个就是一般，因为我这儿做数据科学做的比较多，就是说，一般我们会用就是概率的角度来去分析这种不确定性，或者说它的这儿的。那比如说从你这角度，或者说看你的数据，它大概是一个，比如说一个高维的一个，我用一个联合高分布应该是可以表征的。那我用联合高斯分布来去做，就是也可以用一些鲁棒优化来去做嘛。然后和你这种的它的这个区别是什么？大概这两个问题啊。
好，谢谢张老师的问题。哎，好，它首先第一个就是这个分布上的问题嘛，就是您也可以看，就是这个分布，它其实不是一个均匀分布，它是一个类似于这个联合高斯分布的一个分布，所以它有一些比方说这些 outlier 是可以被怎么说呢？被这种data driven 的方法剔除掉的，因为它和其他的一些数据点距离上比较远，就是可能是存在一些误差。然后对于这些数据量的问题，就是这确实是怎么说呢？就是能源转型的一个怎么说？数据上样本上有一个问题，因为没有这么多的历史数据，而且特别久远的历史数据，我们也不方便拿来用，因为可能和现有这个能源系统差的也比较大。然后这是一个误差。
这个我补充一下，其实我的意思是这个，就是说，如果你用
啊，
一个联分布形式去表征的时候，其实你并不需要太多的，或者说那么多的参数要去评估的参数，因为它的分布形式给定了嘛。然后可能就是高斯联分布，你去每个 item 它的那个 mu 和 theta 去评估就好。但是如果你用这个形状去割的话，它的这个需要评估的参数就非常多。你如果需要评估参数多，意味着你需要的数据量就大。对吧？就是说，比如说我们要评估100个参数，我们的数据量起码也得超过100个，你才能评估。你要99个，它对吧？所以就是说，你评估的参数越多，它其实你需要数据量越大。也就是说，当你就刚才你说的，就是说现在能源转型，特别这个，其实我没有那么多数据，在没有这么多数据的情况下，用这种方法或者说评估这么多参数，它的这个优势。我觉得这个是我就是之前看这个一个感觉，但是如果假如说你给一个鲜艳，比如说它是我用联合高分布来去做，然后你比如说保留几项，它的这个就是说要去评估的参数可能这个数量上要小于你这块儿，那是不是它是更精准的一种办法来表征它的这个就是 uncertainty？对对对啊，我这个点是的
谢谢您补充啊。它这个其实您看，就是它有这么多的面切出来，但实际上它的参数就那么比方说 DPM 就是一个怎么说呢？表征它范围的一个参数，然后像 KD 可能也就是2个参数，所以它尽管是你可以看到它有这么多的面，但实际上我们最后确定的参数就是1到2个，然后从而保证它最后达到这个90%的data coverage。所以就是不是说有这么多的面，我们最后要确定这么多的参数，是这样。所以说我们并不是需要一个特别大量的一个数据，就是类似您刚才说的，像联合高斯分布的话，其实也可以用 stochastic programming，这个也可以就是类似的有解决这个 uncertainty 的问题，是这样。但我们这个是对我们可能文章里没有明确说，因为它用到的这不同的 uncertainty set，实际上最后需要调的参数就是那么比较少的一个数量，尽管它最后可以导致有这么些怎么说呢，不同的 hyperplane 最后导致这个 uncertainty set。 是这样，对，
明白。
所以说不是对，所以说不是一个比较 arbitrary 或者人为可以去调整的这么一个怎么说这么不确定级 uncertainty set。是。
好，谢谢。
好的，好，谢谢您的问题。
我看咱们线上的听众也有提问的啊，就是说希望那个赵宁同学能再介绍一下这个 DPMM 方法，看看可能之前在这个细节方面介绍的，可能大家觉得想再听一听。
是这个 DPMM， 我可以稍等，把这个文章调出来。它是用了一个叫 variational inference algorithm using DPMM with DPMM， 是用了这篇文章的一个方法。总的概念就是它是通过一个怎么说呢，比较少的参数，然后能够得到这样一个基于 DPMM 的 uncertainty set。你们可以看到，就是这些集合里面是它一个 uncertainty set 是不同像几个 hyperplane 最后切出来的。然后我们的目的就是要通过这个方法来得到这个定义 hyperplane 的一系列不等式，然后最后得到这个 uncertainty set。然后如果感兴趣的话，可以看一下，一个是这篇文章，还有一个是对，其实最基础的方法就是基于这篇文章。
好。
然后对，如果有那个具体的这个 uncertainty set 建立方法特别感兴趣，可以就是联系我的一个邮箱。我看看在这里这里面稍等，是 nz225@cornell.edu。
我的理解是，咱们的这样的一个等于不确定性集是以这种超平面的形式，一组超平面的形式割出来的，是这样吧？
是，对，因为它是一组等式，相当是。
这样能保证我们这个不确定性集的这个是凸的，是吧？
对，是。
好，
是您的理解非常对，非常好。然后 how many variables? How many are integer? How do you solve it? 是。然后这个具体计算的一个时间是在这里。然后 solve 的话就是用一个Windows 的一个工作站，然后用程序是用 GAMS， 然后求解器用的是 Cplex。然后 how many integer 这个具体数量我不是特别清楚。这个可以就是你看文章里面有就是具体的一些参数。是。
好，就是我看到咱们在之前您的介绍里面也提到了这个储能，我想了解的是，就是这样的一个储能，我们有没有具体的考虑是哪种类型的储能？因为现在储能的类型也比较多，有功率型的，如果按我们的这个讲，还有这个能量型的，甚至现在大家也看包括这种就是长周期的储能，就是这个在这种年的时间尺度上来进行这种能量调度和平衡的储能，比如说氢能可能被认为是这种可以用于这种长时间尺度调节的这样的一种储能方式。就是我想知道的是，我们的研究有没有针对这种储能，我们再做一些细化的规划的工作，就是我们的方案里面是如何考虑这些储能的。
好，谢谢您的问题。就是储能在这篇工作里面考虑的是有锂电池，有 flywheel， 还有一些其他的。然后主要是最后的结果是锂电池比较，因为它的经济性比较好，然后特别是对这个怎么说这个时间尺度上比较合适。然后另外就是关于储能比较深度的研究，因为这个是在年尺度上的。我们在今年年初还有一篇文章是规划电力系统脱碳的这个同时，考虑到以 小时为尺度的一个发电，还有这个电池的充放电的平衡，或者储能系统的充放电平衡。那么这个就是同时考虑了以年为尺度的这个容量的变化，包括发电容量和储电的这个容量，还有就是以小时为尺度的这个电力系统的这个平衡的一个变化，在这个多时间尺度上同时进行了一个考虑。然后那篇工作里，我们的一个发现就是很自然的，就是储能能够帮助我们调节这个能量一个分配，比方说白天太阳能可以发电，然后最后我们储存到晚上再使用，这是一个小时尺度有一个结果很直观的可以看到。还有一个就是我们通过这个不同的场景对比，我们发现就是利用储能设施可以比较有效的减少这个电力系统脱碳的经济上的压力，最后就是减少了脱碳的总的这个成本。然后所以就是就是还有年初的一个文章，如果大家感兴趣，可以去看一下。然后
因为这两篇文章关注的时间尺度，我觉得可能是不一样的，一个是在年，一个时间尺度上，一个可能在我们这个月啊，甚至更细的每天的这个这种能量的这种平衡或者是调度。所以我想了解的是，在这两个不同的时间尺度下，我们的这种储能的规划的结论是否一致，或者说有哪些区别的地方？
是这样，一致的地方就是因为我们规划的都是怎么说呢？就是最近近30年或者20年的一个系统的变化。那么这个时候，在这个尺度下，我们两个工作最后都发现锂电池是比较优异的，因为考虑到它综合的这个生命周期，包括它的充放电的这个效率和经济上的一个平衡，在这个时间尺度上，十几年、20年甚至30年的尺度上是比较合适的。然后这是我们比较共通的一个结论。是的。然后然后目前就还是先这样。
好，好。
好，
就是我看线上有大家在问，就是说，为什么使用这种鲁棒优化的方法，而不是这种，随机优化的方法去考虑这种，能源转型的不确定性？其实这个我也是想问，有两个问题。第一个就是说，和这个我们线上的这个听众的想法是一样的，就是说，从方法上来讲呢，鲁棒优化是不是会有这种结果会导致结果偏保守啊？这是我们一般的认识，可能这个也许这个不太准确另外一方面就是这种不确定性呢，就是说我们考虑了哪些不确定性有些不确定性，比如说我们这种能源这种政策的不确定性，或者这种发展的不确定性。刚才您说这个锂电池可能认为是这个比较这个经济的，总体来讲，这个是最佳的一种储能的方式，但是可能会随着这种技术的进步或者这种造价的这种成本的变化，可能突然会使得某些储能一夜之间可能去取代，有没有这种取代这种锂离子电池的这种可能？那我们的模型是不是能够处理这种这种不确定性，这种变化？就是说我的这种成本的变化，这种政策的变化，比如说我们还有一些技术的发展的这种变化。当然，这可能超出了这个我们要讨论的问题这个，请那个。
好，谢谢雷老师和这位同学。首先是这个用 stochastic programming，它就是其实这也是一种处理不确定性的一个方法。那这个的前提就是我们需要知道它怎么说不确定性的一个随机的分布嘛。然后特别考虑到能源系统它特别可能历史数据比较少，总的样本量比较小，我们可能很难得到这样一个准确的随机的这个分布，所以可能应用 SP 有一些困难。当然，如果有这个分布的话，SP 也是很好的一个方式。然后不确定性的对不同不确定性的种类，比方说您刚才说的政策上或者技术上的进步，这个。然后对于技术上进步，我们可以就是怎么说？因为我们考虑的是未来10几年，然后我们对每个技术有这个 未来的一个效率和一个怎么说成本上变化的这么一个预测。如果要考虑技术上进步的话，可以就是将这些技术参数的值进行一个修改，可以反映这个技术上的变化。然后政策上的变化就是可以引入不同的比方说限制条件，像我们这里有这个不好意思，像我们这里有这个怎么说呢？不同的政策目标的这么一个条件，也可以在这些条件里面列入一些政策性的一些条件，这个也是就是可行的。当然，这个还需要以后的再进行一个研究。是。
好，还有就是刚才大家提到的，就是这个为什么用这个鲁邦优化而不是随机优化或者其他的这种考虑不确定性的方法？这个能不能再请您补充一下？
是，就是像刚才说就是随机优化，因为怎么说呢，能源系统它怎么说，还是过去的时间它的怎么说呢，样本数据主要来自于一个历史数据，但是我们历史数据的量，因为我们要考虑到它历史和现在能源系统的一个关联，所以它样本量并不是说可以大到特别好的找到这样一种怎么说随机分布的这样一个量级，所以可能用 SP 可能存在一些怎么说挑战吧，或者说如果有这么多的数据的话，那 SP 是一个比较好的方法。然后对于这个鲁邦优化的一个保守性呢，就是我们可以通过控制这个不确定性级的这个范围来调整一些，就是保守的程度。像比方说这个工作我们是 data driven，就是数据驱动的这个不确定性级，我们是考虑到它覆盖90%的情形，这样优化可以去掉一些 outlier，去掉一些特别极端的一个数据点，可以减轻最后结果的这个保守性。但是同时对绝大部分的非极端的这个情形仍然是一个适用的。是。
好，就
一些这样
是
的调整。是。
好，就您也提到这种极端情况，其实我特别现在就是大家对这个能源系统，除了这个能源的转型以外，还比较关注的就是能源的这个 resilience，就是能源的我们国内叫弹性或者是韧性，就是说像您说的，就是往往是这些极端的条件或者极端的场景，往往会是我们对我们能源系统造成这个重大的这种损失的一个条件。像我们发生在加州这些停电，都是由于极端的天气啊或者极端的各种情况来造成的。那我们的这样的一个，如果把这些极端的情况或者没有充分考虑这种极端情况的时候，那我们这规划方案是不是能够经得起这样的一个长时间的这种考验？
是的。极端的一个情况就是，因为也有就是专门做怎么说 resilience 这方面的一个研究的一些成果吧。然后因为我们这里是没有怎么说没有针对性的考虑 resilience。那么对于鲁邦优化来说呢，就是它的极端情况就是像刚才张老师说，它可能更多代表一个边界，就是你表示如果这个极端情况是在这些数据点里面有反应的话，那么这个鲁邦优化可以考虑到这种极端的情况。是这样。
好，非常感谢。
李老师，不好意思打扰一下，我赵同学，对，我最后有几个 comment 是吧？就是这事儿，就是说我其实还是怎么说呢？就是说对这个东西，就比如说线性来去做，因为我做数据比较多嘛，然后用线性的话，我们因为它本质还是你用线性的东西来去割，虽然就是说你中间可以用一些指标 indicator 来控制这个怎么割的方式，但是它本质的数学表征还是用线性的这些面去模拟这些数据点啊，相当于，所以它的就是从我们这儿感觉它的本质的参数量还是在这儿，就是说比如说用线性的话，它肯定是参数多的。然后那我也理解，就是说你们要保证一个它的形状是凸的，然后去做接下来求解的时候好算嘛。其实上次好像尤老师讲的时候， 那阵儿我们也在想，那阵儿在推也没，就是说可不可以用椭圆呢？因为比如说我们用椭圆切的话，因为椭圆切的话，它更符合它的这个，比如说高斯联合分布它的形状，对吧？就是说你高斯联合分布的话，它其实这些点它可能更趋向一个椭圆，包括你看你切的面，它也是近似一个椭圆嘛。
对，
如果用椭圆切的话，应该可以节省很多的参数，就是从本质上来节省。当然，就是说我们一些算法可以就是说通过调一个参数就可以确定很多参数，但是本质上来说，它的这个模型表征能力可能更强，对，或者说一些，我觉得对，可以，我们这可以接下来聊一聊，如果有一些，因为我之前也做过很多这个，也是类似的，就是我们有很多点，然后去找它那个中文叫啥，就是用很多椭圆来去切一个它的一个交集椭圆，然后用那个交集椭圆来去评估，这个也是比较成熟的一个方法，也可以，我也看一看你列那文章，看看就是说它的实用性，或者说一些，对，可以再聊一啊。
谢谢张老师。
啊
是我们其实也对，像您说的就是椭圆嘛。我们之前也考虑到用这个 SVC 去做这个 uncertainty set，因为它最后support vector clustering 最后出来是一个怎么说呢，一个类似椭圆的 uncertainty set。但是这个问题就是用 SVC 会导致，因为我们考虑了未来10几年，导致它怎么说呢？就是 uncertainty set 的量特别大，然后又因为它是一个MARO，导致我们需要用这个affine decision rule，最后使得就是 uncertainty set 一个是 constraint 特别多，然后同时考虑到用 affine decision rule 之后，这个问题的规模会变得特别大，然后最后导致没有办法求解。这个问题可能是自己有自己的特点，所以就是对当时没有用这个椭圆。是
明白
是，但是用椭圆应该是更贴近这个数据点的。是。
明白，好，谢谢。
好，谢谢张老师。
好，感谢张老师，感谢这个赵宁同学。我看看也有同学在问，就是说这个极端条件下的这个系统的韧性，这刚才那个咱们已经回答了啊。那咱们今天这个时间也差不多了，那个非常感谢非常感谢线上参加的各位老师、各位同学，当然也非常的感谢赵宁同学介绍他们这个非常有意思的这样的工作。我刚才看了一下，我们这篇文章是在21年，但是我不太清楚是什么21年大概什么时候这个建刊的或者录用的。
印象是年中附近吧，好像。
那我看在我们这个不到1年的时间里头，我们已经在 Scopus 已经引用了26次，说明还是一个非常有影响力的一个工作也欢迎大家这个关注我们的这个 ADAPEN 的期刊和后续的这个 Undervisions 的相关的青年学术论坛。好，我们今天的这个论坛就到这里。张老师，您那边还有什么？
谢谢，没，好，谢谢李老师，谢谢赵老师，
好，谢谢大家，
拜拜，
再见，
李老师再见，
再见。